Go.
Hello!
Hello, Mr. Aaron, Mr. Ryan. How are you today?
Dad.
Good. Okay. So today we still talk about this binary tree. Okay. So what's binary tree? Remember?
It's a tree which is
We
the
don't know.
opposite way,
Uh-huh.
and it's with numbers.
Okay. So what's binary means?
2.
2 mean. Okay. So it means that for each node it can have a maximum two kids, and for each kid, how many parents does it have?
1.
At most 1, and except
Root.
root. Where are the leaves? What are the leaves?
257.
2, 5, 7. Because they do not have any children. Okay. So how about if I give you this binary tree? Any binary tree, I want you to find out I want you to count. Okay, or find out how many kids are the only child of their parent. So which one
What
are
does
the
that mean?
only child of the parent?
Huh?
Only child of the parent, for example, like which one is the only child in this binary tree of their parents?
Only child.
Yeah, there's 1. Only child means the parent has only only a single child. Okay, so which
4.
one? Yeah. No, because 4's parents 3. It has 3.
1.
7. Come on.
Huh?
Look, because 7 it's the only child of 4, right?
Oh yeah.
Yeah, it doesn't have the 4. Any others? If I put another one here,
2.
if I put another here, then 2 is the only child. No. This one. This one is the only child. Sorry.
It's so
6.
confusing.
No, not confusing. So the only child is that 6 is the only child of 2, right? Because 2 has only child.
What
Right?
if there are 2 ones?
2. Sorry, what 2 what?
2 only child ones.
2 only child. Oh, okay. So this only is not means the only in this binary tree. It means that the only child of its parent. And I want to count how many of these. So in this case, there will be 6 and 7 because these 2 are the only child of their parents. Am I right? Does it make sense? Yes?
Yeah.
Okay. So how can we count this? We would just return 2. For example, there are 2 only child.
We can do.
What?
It's 5 1.
5? No, because 3 has 2 child. Does it make sense?
Yeah.
Okay.
Okay, so a leaf. You check all of the leaves first, I think.
Yeah, but it doesn't have to be the leaf thing, For example, if I put another note here, like 9. 9 is the only child. 6 is only child of 2. So you have to include 6, 9, 7. So that's 3. Okay, it doesn't have to be the leaf, right?
Yeah.
This is only the child, the only child of his parents. It doesn't have to be the leaf. So how can we do this? When we talk about a binary tree, how many ways are we talking about to travel?
Breakfast search. Breakfast search.
Okay, so let's do this breakfast search today, okay? Yeah? So
And
we
tomorrow
visit,
breakfast search.
Yeah.
Tomorrow.
So we visit the binary tree in level by level order, which is the breakfast search, yeah? So which order if you're going to the breakfast
1,
search?
2, 3, 6, 4, 5, 9, 7.
Well done. And what's the breakfast search in the order?
1, 2, 6, 9, 3, 4, 7, 5.
Exactly. And in order to use the breakfast search, what kind of data structure are we using?
Oi. Q or stack? Something
Sorry?
like Q or stack,
Q or stack? Which one?
I guess.
You're not guessing. Q or stack?
Okay.
When we talk about the breakfast search, is one of them is stack, one of them is Q. Come on.
Q.
Q. First in, first out for the Q, right? Remember? For the stack, we're using breakfast search, but usually we implement it in recursion, and that involves the stack. But it doesn't have to. We don't have to deal with the stack manually. We can use the recursion. Let the compiler to generate this coding stack, right? Okay.
Yes.
So breakfast search. Okay, so we have a queue, and first in Q is first in what?
First in, first out.
Okay, so yeah, exactly the queue. Look, this queue Q-U-E-U-E, yeah? Q is the only letter that's pronounced in this word, yeah? Q and all other letters are silent. It means that the Q is being served. Only the head of the Q gets being served. All others need to wait quietly, right? And when the new element join, they join at the end. When the queue, when the next element to be served is the head of the queue, right? Okay, so at the beginning, we want to initialize the queue with which element in the binary tree? Which element in the binary tree? If we want to do this, implement it perfectly. No, but look, at the beginning, the queue is empty, so root. Yeah, we put a root, which is 1, right? Okay?
Then you put in.
And then we repeat until the queue is empty, alright? So every time if the queue is not empty, what should we do? We take one element out of the queue, yeah? The queue, yeah? Take it out and push its
Kids.
which is
2 and 3.
2 and 3. Okay, and then next one,
2.
take a 2 out, the head of queue, and push its kid. Which
6. Only has 1, so.
yeah, I only have one, yeah. So, but in order to yeah, this is a buffer search, but in order to tell which, does it have a, is it a only try, we have to record the number of tries when we're expanding, right? So, for example, like 3, yeah? I take 3 out, yeah? Yeah? When I take a 3 out, I push the kids array. At this point, I know how many kids the 3 has, right? It's 4 and 5, right? Alright? Yes? So when I push the 4 and 5, I also need to know, okay, its parent 3 has 2 kids, right? Okay, then 6, I take it out, I push the 9, right? But 6, I know it's only 1 kid, yeah? When I push the 9, I also notice it's 1. So look.
Also 2.
Yeah, look, when I take a 4 out, but I don't know it's coming from a parent which has 2 kids too, right? So I don't count this as an only child, right? Yeah, but I keep expanding. 4, I push the 7 in, right? I put a 7 here. But I also know that when I do this, I know how many kids does the 4 have? 1, right? Yeah. So when I push 7, I also notice this is coming from 1 child parent. Right? Are you okay?
Yeah.
You want to speed up? Good. So one child parent. So in this case, we're doing this. We accumulate it. Yeah.
Yeah.
Does it make sense?
Yeah.
So let's do this now. Let's do this. Okay.
Banana.
Breakfast search find. Let's do it. Count only child. Okay. Root. Okay. Root. So what are the data structure we used in Python to implement a queue?
DQ.
And what's DQ mean?
Double-ended queue.
Double-ended queue. Yeah, double-ended queue. Okay, so let's at the beginning, if root is none, what should we do? Return what?
Return none. I think
0. Yeah, if you want to count, we return 0. Okay, then double queue and DQ. Q equals DQ, and then we take a list of the initial. So at the beginning we take a tuple, yeah, root, and we set the second element of the tuple array is 0. We mean that it's coming from the 0 parent element, yeah, the parent. If it's 1, it's coming from 1 child parent. If it's 2, it means it's coming from 2 child parent, right?
Yeah.
And then we need to go this answer, count. Answer equals 0. Okay, so look, while Q, yeah? While Q, Eric, we want to DQ, yeah? So we want to have a current now, and then the count is the number of
Why is the NT?
count or any element. This is a variable, okay? Equals DQ. How do we DQ? Q dot what? Pop what?
I think left.
Yeah, left because we DQ, we take it from the beginning, which is left, yeah? Yeah?
Yeah.
And then because why this is this current, because look, the first element is the root. Alright. The second element is the count, right? Yeah. Yeah. Okay, so now look. If count equals 1, what should we do? It's coming from one child parent, so the current node is the one child, right? Only child, yeah?
Yeah.
So what should we do with this answer?
Answer.
We found it, so what should we do? Increment it.
Add 1.
Add equals 1, okay? Right?
Yeah.
And then now let's say,
Awesome.
look, s equals 0. Like we are starting to counting how many kids does this node have. So look, if current dot left, yeah, x plus equals 1, right? And if current dot right, what should we do? Huh?
X.
This means the number of child for the current node. The left node I found it.
Add.
Yeah. Come on.
Equal.
Equal?
1.
Yes. So now look, I know how many kids does this node have, right? And now what should we do now? I need to check. Right? Look.
Yeah.
Then look, Eric, here. I put it here. If current dot left, what should I push it into the Q, yeah? Q dot append, right? Append what? Can you tell me? Append what? There are two things here.
Append left.
Current dot left. And what's the second?
Current right.
No. We are pushing the the count. So what's the count here? What's the number?
0.
What's the number? What are we doing here?
We are.
Counting.
Yeah.
And then what should I put here?
Add.
X. Come on, X. We are counting how many kids this node have.
The value.
Yeah. If current dot right, what should we do here?
Yeah.
If current dot right, what should we have here?
Current right. Q dot append. Current.
Current dot right. Now and what?
X.
X. That's a tuple, yeah. Tuple. Look, tuple.
Q.
Tuple. You use the bracket.
Yeah.
Parentheses. Okay. Parentheses.
Parentheses.
The tuples are immutable, means that when you declare it, you can't change the elements in that. Immutable, yeah. You can't change. Like the string. Like the string in Eric. Look, if you do this P equals Eric, this means that it's immutable. You can't do this. You can't do this P0 equals like right R. You can't do this, right? Because when you declare a string, it's immutable. It means the constant. You can't change it, right? That's particularly in Python, right? The immutable.
I'm
What?
agreeing with right.
Immutable. What's immutable? What's immutable? Mutable. What's mutable mean?
In Zoom, you can't talk, or you can't talk.
No, mutable, not mute. Mute is you can't talk. Mutable means the change. Mutate, okay? So immutable means that you can't change. It stays the same. It stays immutable, okay? Okay, now look, after this we push the kids. And then what's missing here? We have a last thing.
Return
Return what?
something.
Return which number are we calculating?
X.
Answer, come on. Okay, what's the time complexity? Oh, what? What's the space complexity? When we talk about a breadth search, how many nodes are in the node? Oh, n is the number of nodes in
In the stack. No, in the
binary
tree.
tree. Okay, what's the space complexity?
N.
Why are we using the why?
Because the stack.
Not stack. We are not using the stack. We use the
Key.
queue. We are using the queue to store the number of nodes. Yeah, in the breadth search. Okay. Yeah, does it make sense? What you doing?
Vroom.
Okay, so any questions? If we don't want to count, if we want to return it, so look, this answer is a 0. Yeah? If we can change it to Eric, it's a 0. We can change it to a list, and then instead of answer equals 1, what should we do here? Answer dot append what? Current, right? Yeah. All right.
Yeah.
This is to return a list of the only child, right? But you can also do this. You return the child, and then if you want to return the count, you can also return length answer. Yeah? Yeah? It's the same, yeah?
Yeah.
Does it make sense?
Yeah.
Does it make sense? But in this case, you are storing all the nodes. Only try in the answer and then counting it. Okay? And it might be better just to increment the counter. Okay? Does it make sense?
Yes.
Okay, that's it for today. Say thank you.
Bye.
Say thank you and see you tomorrow.
See you tomorrow.
Okay, see you tomorrow. That's it.